So in today's class, we're going to discuss the VLSI design module 2, that is fabrication and MOSFET scaling and small geometry effects. So let us see what are the topics which covers in module 2. So in fabrication, we have CMOS fabrication and layout, VLSI design flow, the various CMOS technologies, and the design rules in order to construct a layout. Along with this, we have second part. In second part, mainly we will going to concentrate on MOSFET scaling and small geometry effects, that is full scaling as well as constant voltage scaling. And we will also discuss about the MOSFET capacitances. So let us move to the introduction. So as we know that the designers need to understand the physical implementation of the circuit because it has major impact on performance, power, and also cost. So before analysis of any of the circuit, the first thing is you need to understand how the circuit is implemented physically, because this physical implementation has major impact when you are analyzing with respect to performance in terms of power and also cost. As we know that, so in order to construct MOSFETs, the major role is transistors. So these transistors are fabricated on thin silicon wafers. These wafers can serve as both mechanical support and also an electrical common point. That one we can call it as substrate. The transistors are fabricated on a thin silicon wafers. These wafers can serve as both mechanical support and also an electrical common point we can call as substrate. So here we can examine the physical layout of transistor from two perspectives. The first one is top view and the second one is cross section view. So what is this top view? Top view is nothing but you are going to see the circuit down on a wafer, looking down on a wafer. Cross section is nothing but you are going to see the wafer through the middle of a transistor and looking at it edgewise. So we have two perspectives. One is top view, another one is cross section view. Top view is nothing but you are looking from down. Cross section view is nothing but you are looking at the edges as well as middle of the transistor. So here you can see this figure. So here it is an CMOS flip-flop with two-phase non-overlapping clocks. So here generally as we are making use of G flip-flops. So this is the first stage and this one we are call it as second stage. So the output of first stage is QM can be given as input to the second stage. So the final output we are getting as Q. So as here we are making use of two non-overlapping clocks, that is pi 1 and pi 2. So here the flip-flop can be constructed with a pair of transmission gate and also an inverters. So next we're going to see cross-section view. That is here the figure shows the inverter cross-section with well and substrate contacts. So as you know that here this figure shows the cross-section and corresponding schematic of an inverter. Here in this diagram, the inverter is built on a P substrate. So this is nothing but your actual inverter. This inverter can be built on a P type of substrate. So as you know that, so the inverter has one PMOS transistor, that is pull up network consists of PMOS transistor and the pull down network consists of NMOS transistor. Here you can see this figure is the schematic diagram of an inverter. It consists of PMOS transistor and also an NMOS transistor. The top of PMOS should be connected to VDD and the bottom of NMOS should be connected to ground. Similarly, the gates of both transistor can be tied together and give as an input A, and drains of both the transistor are tied together and gives us an output Y. So here you can see that this is nothing but the diffusion regions. So this is nothing but N plus source and N plus drain. Here also P plus drain for this P plus source. So here N well region is formed in a PMOS transistor. Here you can see that there will be a three terminals. So this is nothing but source terminal, gate terminal and also drain terminal. Here also gate, source and also drain terminal. So these two are nothing but gates. You can see this is NMOS transistor and PMOS transistor. So the gates of both transistor are connected together and gives us an input A, and the drains of two transistors are connected together and provides us an output Y. Here the sky blue color, this one which indicates the SiO2, a thin layer on the wafer, we can call it as SiO2, and this brown color which indicates the N plus diffusion, and this dark sky blue color which indicates the P plus diffusion, and these lines, these are nothing but polysilicon gate, and this is nothing but metal one. So this is the cross section view of an inverter. So if you are giving input as 0 for the inverter, the output should be 1. If you are giving input as 1, the output should be 0 for an inverter.